Hi, everybody. Ooh, the creepy music is coming out. That must mean we're approaching finals week. Which we are. Holy crap, it's week 10 already. I can't believe it. So we have one unit and a little bit of this unit to go, which should be plenty of time. So our goal this week is to finish all the content. We're going to go through the rest of Unit 15, and then we'll do Unit 16, which is really not going to be a ton of new stuff once we've talked about what solubility is. Like the calculation stuff, we've more or less already done them. So yeah, what agenda items do we have here? There's a quiz that's due tonight. That's for Units 13 and 14. Make sure to get that in. It will close tomorrow. And exam number 2 is this Friday. Remember, if you need your exam moved forward or backward one day, email me. I can do that. You can take it on Thursday, Friday, or Saturday. I can't go further than that because I have to release all the scores at some point, and I do have to wait for everybody's exams to come in before I release the scores. Otherwise, I might unfairly benefit people for whatever reason. What else do I want to talk about? There is a lab. We're going to talk about the lab a little bit, probably Wednesday during the review session. Lab number 5 deals with Unit 16. I'd like to just get all of that done before we even start with talking about the lab. But I think the most immediate thing that is of importance is the last quiz, which is Units 15 and 16. So that quiz number 9, is going to be posted tonight. And what I do, because it's the same situation that we were in before the first exam, but instead of this one being worth points, I set it to be worth 1. And somewhere in your quiz, there's a little box that says, check this box to make Canvas give you 1 out of 1. So it doesn't have a divide by 0 error, because I can't make quizzes worth 0. So what that quiz will entail is it'll be Units 15 and 16. You can take it now, you can take it after the exam, whatever. But its purpose is really just to let you see some of the problems that you'll see on the exam that are Unit 15 and 16 related, and be able to practice them and then see your answers, because it'll open immediately after you've taken it. You still get capped at 2 attempts, so make sure you use them wisely. But you can take them whenever you want to, and it closes, I think, on the day of the final. Which is like a week from Wednesday, so we're very close to being done. All right, we left off last week talking about the limiting reactant. What I want you to do is these 2 questions on the screen here. So I have this equation. I want you to balance it, and then with the information provided, so this much silver and this much H2S, and then excess O2. So O2 you don't have to calculate. You have all the O2 you can need. It won't run out. I want you to tell me the limiting reactant and then what mass of Ag2S you would produce. Now, I want a mass, even though I'm giving you moles to start with here. At the bottom, I have scribbled out a question. In the interest of time, we're not going to solve that. So that you're not going to be tested on that type of question. We'll get to that in 162. So go ahead and answer these questions. First, make sure you have a balanced equation that checks out. Make sure that you double check that you've balanced the equation, because it's not all ones, okay? And then do the calculation. I'm going to give you 5 or 6 minutes to do this, and then we'll go over the results together, okay? And then we'll finish chapter 15. So, see you in a bit. All right, one more minute. We'll go over the answers. All right, let's do this. And then I got to fill in the I got to balance the equation first. So let's do that real quick. So let's see here. So I got to do this, which means I need to do this, which means I need to do this, which means I need to do that. There we go. So that should be balanced. I'm just checking what everybody else wrote. You wrote the same thing that I did, so that's a good sign. Just in case my mental math failed me, which happens more often than I would care to admit. Oh, I didn't actually capture all of the problem here. So. Let's just slide that up a little bit. There we go. All right, so we need to figure out the mass of Ag2S from these amounts of moles. So I'm going to write down the amounts that I have. And then I have this many, 872. All right. And so we have moles of our reactant. And we can easily turn that into moles of the product, which is this, which we can then turn into a mass. We'll follow the same blueprint for both of these. And whichever one we make less of is the limiting reactant. So we can turn moles of silver into moles of silver 1 sulfide. And the coefficients for that, so silver is 4. For every 4 silver I put in, I get 2 silver sulfides out. And then I just have to figure out how many grams there are per mole. So I got to go to Lentech, which I believe I closed. Yeah, I got to open that up again. So give me a second. Oh, I don't know what window I'm in. Too many windows in my computer are open. And I want AG. That's the caps lock. AG2S. And I got 247.80 grams of silver 1 sulfide per mole. So when I type that in the calculator, I get a problem. Oh, there's my calculator. It's over there for some reason. I put it on this. My cats have this box on the couch, and I sat stuff on top of the box, and there was my calculator, which was like, when do I put things on my left? That's not a thing that I do. Apparently, I did it today. And then divide by 4, and I get 3 sig figs, so 17. Oops, not 17 actually, 18.0. All right, so that's what I got for the first one. We do the same thing down here. Wrong. Let's try that again. And this is 2 to 2, yeah? Yeah, so 2 and 2. I mean, 2 divided by itself is just 1, so we'll cancel those out too. And then the same thing that we did above, so I'm just going to copy those numbers right down. And what do we get when we do this? 0.0872 times 247.80. I already wrote an equals. That's okay. There we go. All right, so who was the limiting reactant? It's the one that produced less. So we were limited in this case by silver. We ran out of silver before we ran out of H2S. So this one is the excess. And so we scribble through it, and we don't use it as our answer. We only use the limiting reactant. All right, there you go. So just a quick refresher on limiting reactants. Let me know if you have any questions about that. We're going to carry on to percent yield. Percent yield is a very common thing to do in chemistry because of two reasons. One, it lets you know how efficient your reaction is. And two, it's useful as a conversion factor if the percent yield is known. Now, it's very important to note that percent yield is not meant to be a gauge on your ability in the lab. Not necessarily. For instance, a reaction may have a high yield of 70%. Again, so it's not a grade. Other reactions are extremely difficult to get the product in high quantities, and their yield may only be like 10 or 15%. This is common in organic chemistry if you have multiple products that are possible and you specifically want one type of product. And so your job then is to extract it or isolate it or separate it through some sort of chromatography or whatever. You'll deal with that in 261. For now, let's just introduce the concept here of percent yield. Now, in 163, we're going to talk about equilibrium, which is a situation where reactions compete. You have reactions producing products, but those products are then reactive and could react with each other and produce reactants again. So you won't ever get to 100% yield because your products just decompose as soon as you make them. And your job is to just stop the reaction, which is like, say, isolate the substance before it has the opportunity to do that. Other issues that can come up are things like different conditions. If you heat a reaction too hot, you get other reactions, and thus you get decomposition to other products that you didn't want, and you lose what you're trying to go for. And then the last issue that can come up, which is really the only thing in this list that it can be attributed to a fault of the experimenter, is some sort of error where like you drop your product, or you don't scrape all of like one thing into the next container, or you lose it while transferring, or something like that. So this one down here, this is really the only one that I'd be like, oh, that's not good. You shouldn't do that. I will deduct points. The other ones you have no control over. And so that's okay. Regardless of what causes you not to get 100%, the amount of stuff that you produce is called the actual yield. If you do an experiment and you actually get this much stuff, it is your actual yield. So whatever you weigh at the end of your laboratory experiment, put on a plate and then present to me. I made 10 grams of this today. Your actual yield would be 10 grams. Now, in theory, you should get 100% completion, right? So if we do a calculation and make the assumption that, okay, everything reacts and it all turns to products, then the calculation will tell you the theoretical yield. Everything we've been calculating so far has been a theoretical yield because we haven't actually been doing these experiments. We've just exploring them on paper, right? So the theoretical yield is the math. It's the theory behind it. It's everything we've done so far. When you actually are in the lab, you compare the actual yield to what you should get in theory, and then divide the two and multiply by 100. That will give you a percent yield. So let's suppose that I do a reaction and I'm supposed to get 50 grams. And then I do the reaction and I actually end up getting 40. Then I would say, okay, 40 over 50 is 0.8 times 100%. is 80%. So if this is what I got, and this is what I calculated, then I did a reaction and got 80% yield. Now, this is a conversion factor. Actual divided by theoretical is a conversion factor. So if you know the percent yield, you can figure out what the reaction yield should be for a given amount that you started with, just by doing a conversion. So we're going to explore all sorts of different problems here that look into this concept. So here's our first example. I'm going to react 4.7 grams of hydrogen with excess nitrogen, and I get a product amount of 12.5 grams. So this is what he recovered. So this is his actual yield. This is not from a calculation. This is what he got. What would the percent yield be for the reaction? Well, first what we need to do is we need to figure out what this amount of H2 would produce when we react with excess N2. Do I have the balanced equation? I do. Okay. So let's try that. So we need to calculate the theoretical yield here. So we know that the actual yield, we'll do it in red here, actually, was 12.5 grams of ammonia. The theoretical yield will be whatever the result of our calculation is. So if I have this many grams of H2, and I turn that into grams of NH3 by doing calculations, like we've been doing so far, I can figure out what that is. So let's do that. I don't need to actually delete all that. That's what I want to delete. So we'll start by turning grams into moles. I believe that that's right. I should really just look that up on Lentech instead of... Oh, I was right. Okay. Should have trusted me. That's okay. And then we'll turn moles of H2 into moles of ammonia. We did plenty of this in Unit 15, right? So now we'll use the ratio. So for every H... So I put 3 H2 in, and I get 2 NH3 out. And then 1 mole of ammonia is 17 something. I'm just going to type it in there. NH3. Oops. Didn't have that selected. 17.03. All right, so what do I get for doing this experiment? So if I put 4.7 grams in of hydrogen, make sure you put parentheses on the bottom. I almost forgot. I would have got the wrong answer. So the theoretical yield should be that according to the calculation. All right. I know the actual yield, and I know the theoretical yield, so now I can compute the ratio between them. So percent yield would be actual over theoretical times 100%. And so that'll be 12.5 grams of ammonia divided by 26.5 grams of ammonia. Those units cancel out. Times 100%. And I get 47.2%. So this student's yield was 47.2% for the reaction. Did this student do a good job? And the answer is you have no way of knowing. Any of those factors could have taken into consideration. I personally know that that's a exceptionally high yield. So making ammonia is very difficult without manipulating the reaction conditions into crazy ways to force the reaction to go forward. Also, this is not a reaction that a student would do. This is an industrial reaction. But the purpose is just to do the calculation. So there you go. All right, so now that you've seen percent yield in action and you can calculate it, it's not terribly difficult to do because we're not really doing anything new here. I got 47 for some reason. I think because I had a different number here, but that's okay. I round on my calculator run. No, that number on the screen isn't the same as what I got. I got 26.5. Anyway. Close enough. All right, so now what I want you to do is try this reaction. Now, you're not going to be calculating 80% yield because I have already done that. So this chemist is gathering copper metal from the reaction of aluminum and copper 2 chloride. And so she gets 87.7% yield and 96 grams of aluminum. So when you set up your percent yield equation, what parts do you know? Well, you know the percent yield. This is a number. And if you use this number to calculate something, you're going to fill in one of these things, right? And then solve for the other one. So what I want you to do is do the calculation and figure out what 96 grams of aluminum theoretically could produce. Okay, I've given away the answer. And from that, solve this equation so that you can figure out what the actual yield was. So go ahead and try that. I'm going to give you 5 minutes to mull it over, and then we'll go over the answer and in just a bit. So see you in a little bit. One more minute, we'll go over the answer. All right, so let's go back over here. Yeah, we'll just wind this down. All right. I didn't balance the equation, so I need to do that real quick. So that's going to be a bunch of 2s and 3s. So here's a 2, here's a 3. That's wrong. Hold on. Try again. So here's a 3 and here's a 2. So this is 3 and this is 2. There we go. Excuse me. All right, now I can go back to Photoshop here. All right, so I have 96 grams of aluminum. And so we can turn that into moles of aluminum. So 1 mole of aluminum, according to the periodic table, which I've covered by a calculator in my phone, 26.98 grams. And then we'll turn moles of aluminum into moles of, what do we want here? We want copper, right? So we'll do that. And then let's see here. How many moles of aluminum go in? So we put 2 moles in of aluminum. We get 3 moles of copper out. And then where's the molar mass of copper? 63.55. Gotta get my calculator back out. 98 times 2. There we go. So I got 339 grams of copper. And again, this is the theoretical yield. Let me just double check my numbers here. 96.3, 63.55, 26.98, and 2. Okay, cool. All right. Now we have the formula for actual and theoretical yield. I need to solve for the actual yield. So what I'm going to do is I'm going to do this. We're going to do some algebra. So I'm going to divide both sides by 100%. So I get percent yield over 100% equals actual over theoretical. And then I can just multiply both sides by the theoretical yield to get rid of that, right? Because I would do this. So my percent yield was 87.7. My 100% just is 100%. These percentages cancel out. Times the theoretical yield of 339 grams of copper. And I get 297 grams of copper. There you go. So, yeah, even though it looks like strange because we put 96 grams of copper in. Note that you are working with something that has a higher molar mass, so per mole you're getting more stuff. And also the ratio is 2 to 3. So for every 2 moles of aluminum you put in, you get 3 moles of copper out. So you get way more copper atoms available, and each copper atom weighs way more. So you get a very large number as a result. And so that checks out. So that's what I do when I'm checking my answer. I like a good initial reaction is like, wow, that's a really big number, relatively speaking. Where did all that mass come from? But if you can go back and rationalize it and say, oh, yeah, okay, these atoms are like almost twice as big or more than twice as big. They're like almost 3 times as big. And I get more of them. So both of those will lead you to getting a much larger mass. All right, that's percent yield. So you can do all sorts of problems with this sort of stuff. Oops, I didn't mean to flip through that. How much time do we have? I'm going to leave these problems for you to do on your own, and we're going to move on to Unit 16, because I just want to make sure I get through the Unit 16 stuff over today and tomorrow. So go ahead and write those down. These are the same 2 types of problems that we just did. And if you have any questions about the answers, poke me on the Discord, and I can do my work on the on this, and then just paste it into the Discord. So, but we get our hooray work here. So hooray! All right, I think that might be the last time we hear that, because the last one is just congratulations, you've completed chemistry 140. So let me get, oh yeah, until 161. Yeah, then you hear it all over again. And it should be on the screen. There it is. Okay. Okay, I got everything I need to. Oh, wait, no, I need one more. I gotta do that. There we go. All right. Unit 16 is all about solutions. Solutions are important to understand because they're a very practical way to do chemistry. Doing reactions between 2 solids is very difficult, since reactions can only occur where things can contact each other, right? So if you have stuff dissolved in a solution and then you mix the 2 solutions with the reactants you want together, they react very readily. So you're going to be doing a lot of solution chemistry by virtue of this is just the most accessible phase. The next accessible phase would be the gas phase. But gases are also solutions, as we're going to find out. So we're going to start with a video. I'm going to see if this video will actually show up, or if YouTube's going to tell me, like, hey, your browser is up to date. Okay. It seems to have worked, so now I can capture this. This one. Okay. Not quite right. All right. We're going to put water and sugar together. On the left side, I got to cover up the chat for a second here. On the left side, we have water that is very warm, and on the right side, we have water that is actually, I don't know which one's which. You'll see it here though. So there's sugar. And when you drop it into water and you just kind of let it sit there, something interesting happens. And I'm going to fast forward it a little bit so that you can see it in more of a time lapse. What do you see is happening to the sugar on the left, which is the warmer water? And then the one on the right is also doing this too, but it's just going much more slowly. So you can see that if we speed it up, it looks like it's disappearing, but it's not actually disappearing. What is happening is that all of the particles that are congealed together in our solid are individually coming off and being dispersed into the liquid medium. If a substance is capable of doing this, we describe it as soluble. A substance that collects at the bottom of the container and does not dissolve at all, like, for example, like mud in water. If I drop if I scoop up muddy water, the silt and soil will just sink to the bottom of the container, and it doesn't dissolve. We would call that insoluble. So those are our two extremes here. We have soluble, which means it doesn't dissociate, it dissolves into the solution. It may dissociate, doesn't necessarily. And then we have insoluble, which means that it just sticks around, it clumps together, it doesn't seem to dissolve. It remains as a solid in the vessel that we're looking at. All right. When you dissolve stuff, the result is what's called a solution. A solution is any mixture of at least two things. You can have more in there, but two is the minimum. If you have less than two, so if you only have one thing, it's a pure substance. It's not a mixture. So, a solution requires you to have something that dissolves, and then a medium to dissolve it into. The solute is what you are dissolving. So this is the substance that you are working with. And the intent is to dissolve it. And then the water, in this case, would be the medium in which we're dissolving our solute. So those are our two terms that we're going to use. We have the solute, which is what we're putting in there, and then the solvent, which is what we're dissolving it in. Now, don't mix up the terms. It's very easy to reverse these. Together, we get the solution. That's like a metaphor for life, right? Together, we get the solution. I might have to, like, put that on, like, a t-shirt or something, or a poster. I'm sure someone's already done that. All right. Now, when you mix together different substances, if you mix them completely, you'll get a homogeneous mixture. Now, the number of things that you can mix together varies. In fact, it varies by phase, even. Typically speaking, we think of liquid solutions because those are the most common. So, like soda, carbonated water is a solution. Your orange juice is a solution. Milk is a solution. But you don't necessarily have to dissolve only liquids or solids into a liquid solvent. There are other things that are possible. So, for example, if everything is a gas, you make a solution. In fact, air is a solution. You're breathing a solution right now. The solute in air is oxygen because it's the thing that you dissolve it into. The thing that there is most of is your solvent, because you need some medium to dissolve stuff into. So we define that as what there's more of. So that's something to note. So solvent is, by definition, what substance there is most of. Substance. There we go. So for air, that would be nitrogen. Nitrogen is your solvent. For a solution like, say, soda pop or carbonated water, the solvent would be water because it's the majority component. Now, you can have solid state solutions too. For instance, if you mix two metals together and form an amalgam, such as iron and, say, chrome to get like steel, or for example, or carbon to get steel, then you get an alloy, and alloys are all solutions. So these right here are all solutions of solids. I missed one. I'm sorry. I didn't actually extend this long enough. Why did you do that? I don't know. Specifically, the results that you get when you mix two metals together, these are called alloys. So silver mixed in gold is a specific alloy. It's called electrum, which is why in Dungeons & Dragons 5e, electrum coins are worth half as much as gold coins, which is stupid. And nobody uses electrum because everything else is powers of 10, but electrum is powers of 2. But electrum is very pretty. It's it looks almost kind of like a white gold. It's just a stupid currency in D&D, so ignore it. But other alloys exist, so like things like pewter, brass, bronze. Those are all examples of solutions of metals. How much can you dissolve in a solvent? For our purposes, we're going to move on to just aqueous solutions. So aqueous solutions are solutions where the solvent is water. That's going to be the only solvent that we really care about right now. And our task for this next little bit is to discuss how much can be dissolved in a solution and then all of the different ways that we can manipulate that number. So what I'm going to do is I'm going to link the solubility table here for you. I'm going to click on this. And you can look at this if you want to, because we're going to take a break. So I'm going to put the solubility table in here. And then I'm going to put it on the screen real quick. So on the screen is a solubility table, where scientists have looked at every compound that they can imagine in water and seen how much of it dissolves. And so there's all these numbers here. And this is just like stuff that people have done. And these numbers have been recorded, and now they're on Wikipedia forever, right? You'll notice that there's a lot of blanks. So maybe if you're bored one day, you could be like, well, I'm really interested in cerium-3 hydroxide, so I'm going to just do a bunch of experiments to test that. And like, sure, whatever. But you'll notice that there are some patterns in these numbers. You can just look through it if you want to over the break. Like, or don't, like, take an actual break, right? But when we come back, we're going to look at what those numbers mean. I have a graph of those on the screen here for some selected ones. And we're going to see if we can do some interesting stuff with this and understand a little bit more about solubility. So we'll deal with that in 10 minutes. So I'm going to put the music back on here. And I will catch you in just a little bit. So see you then. All right. Hope everybody had a nice break. Let me turn this down. If my computer will pause it. There we go. Sorry, browser was laggy there. Hold on. I gotta clear this. There we go. Okay. Why did that happen? Oh, okay. Sorry. I had a pop-up, and I was like, I did not expect this window to appear. It's because I hit the wrong thing. Okay. So you can see here on this table that this is measuring the amount of stuff that can be dissolved in 100 grams of water. And so that's going to be our baseline for how much we're going to be able to dissolve into. So we're going to have a bunch of beakers that have 100 grams of water. And what we're going to do is we're going to use different substances, and then we're going to measure them at different temperatures. If something dissolves completely, then there's not going to be any visible solid at the bottom. But as soon as I hit a limit on that solubility, a solid will start to appear. And so we're going to see this effect in just a second. I think it's in the next few slides here. Hold on. I got to check real fast. Like, I should have some pictures. Yeah, it's coming up on the next few slides. But what you can see here is that almost universally, solubility goes up as you increase temperature. Now, there are some substances that do not follow this rule, and this is has to do with thermodynamics. Like, dissolving the substance would be endothermic, and so it doesn't actually happen. We're going to talk more about thermodynamics in 162. In fact, that's kind of the whole point of 162 is thermo. But yeah, we'll come back to that. On this slide, I have some definitions for solubility, and I don't really personally like these because soluble versus insoluble should be pretty obvious, and you don't need to ascribe a number to it. And the one I really don't like is this one in the middle, which I'm going to kind of scribble through. So, slightly soluble, not super important for this class. We're not going to define something as slightly soluble. Something is going to be insoluble if it doesn't visibly dissolve, because you're always going to be putting more than 0.1 gram in there. And something is soluble if it does visibly dissolve. Generally speaking, you're going to put like a bunch of stuff in there, and either it will dissolve or it won't. Some things do take time, and they might need a little bit of heating. But generally speaking, any substance that we're going to be working with in the laboratory will have visible dissolution occur. And then we could just say, okay, it's soluble. All right, so what does this visually look like? If you add stuff to your container and the substance you're adding has a color to it, for example, this is copper sulfate. Copper sulfate is pretty soluble in water. And anything that dissolves will make the solution turn dark blue. Now, if you pour tons and tons of the stuff in there, eventually it stops dissolving. And that's just because you have so much in there. When you hit the point that you've dissolved all a solution can hold, a solid will crystallize and collect on the bottom of the container. If this is visible, the solution is said to be saturated. A saturated solution has the maximum amount of solute that can dissolve. Now, if you don't put the maximum in there, like say you put a little bit in there, further solute could be dissolved in there, but we haven't given it an opportunity to do that by adding it yet. So, a solution that can potentially hold more would be unsaturated. An unsaturated solution is very obviously different from a saturated solution by virtue of having a solid at the bottom, but also the intensity of the color should be much deeper. If your solution is colorless, this doesn't really help you, and therefore you can't use that as a rubric. But if your solution does have color to it, this will help you determine how much has dissolved in the solution. Now, what does it mean for something to dissolve? This is actually a more advanced topic that we're not going to talk about in much detail until we get to 163. But for things to dissolve, they will interact with water and dissolve out into the liquid phase where they're surrounded by water. And I'm going to put a bunch of dots here to represent stuff as dissolving. And these dots will be all over the place. And they can move in any direction they choose to. I mean, it's essentially random. They're not actually choosing. But what would happen if one of these molecules or ions or whatever not decided, again, I'm anthropomorphizing this. What if one of these molecules randomly just went in the direction of the crystal and bonked into it? It could reattach, right? And what ends up happening is when you reach a saturated solution, the speed at which stuff dissolves is equal to the speed at which it recrystallizes. Sorry, I'm trying to do this. Wow, my handwriting sideways is not great. I'm trying to do it without turning the tablet because that doesn't actually work. You know, that's just so hideous, I don't want it to even be there. We'll just do this. Recrystallize. When you have this equilibrium, where the amount of stuff dissolving is just as fast as the amount of stuff recrystallizing, that's when your solution is saturated. Now, why do you hit an equilibrium? Well, initially, everything is dissolving because it can. But if you don't have any of these dots up here, because stuff hasn't dissolved yet, I'm just trying to erase most of them, then you don't really have much opportunity for things to recrystallize, because there's just not enough for it to happen yet, right? So things will keep dissolving until there's so much in the aqueous phase that it begins to crystallize faster and faster and faster. And at that point, you hit saturation. Down here in the unsaturated example, we had a solid that was here, which I'm going to write as dotted lines. And it has since dissolved into this phase. But if something tries to redissolve, it can't. There's no solid to crash into to crystallize with. And two ions coming together to recrystallize isn't enough. You need more than that. You need a surface where there's tons and tons of ions to get other things to stick to them. So in an unsaturated solution, everything just stays in the aqueous phase. And you don't see any solid at all. So that's just another description of saturated versus unsaturated from a more molecular-oriented perspective. And again, we'll go into that in more detail in 162 and 163. Now, using that logic that we just had, if we increase temperature like this, and we go back to this slide right here, increasing temperature makes things move faster. We haven't really talked about temperature much in this class, but temperature can be thought of as the speed limit for molecules. A higher temperature means that your molecules move faster and faster and faster. And if things move faster, they're more willing to break free of the solid phase and enter the liquid phase. So if I heat this up, more will dissolve out. And that means that more will be up here in the aqueous phase. So solubility tends to increase as you raise the temperature. Not always. Sometimes adding heat does other thermodynamic effects, like make the solution cold, which would then slow it down. That seems weird to say, but adding heat means that the reaction absorbs the heat and from your source and then also the surroundings. So you add a little energy and then more is absorbed than you added, and the result is the solution gets cold. This would be like, for example, a hot pack. Not a hot pack, I'm sorry, a cold pack, where you mix two chemicals and it gets very cold. Now, if we can control the amount of stuff that's dissolved, we can do an interesting thought experiment. And so what we're going to do is we're going to do this. We're going to work with KNO3 for this thought experiment. And so what I'm going to do is I'm going to make a solution at 20 degrees Celsius. And the way that I'm going to do this is I'm going to add enough potassium nitrate so that I just barely get a saturated solution. And so that would be 30 grams. So if I do this at 20 Celsius and 30 grams, the result that I would get would be saturated. And that checks out because that's where the line is, right? If I were to add more than this, so if I added like say 40 grams, 30 of it would dissolve and then the remaining like 10 or 12 or whatever would just collect at the bottom of the container. So we're not going to add more than we need. We're just going to add that much. Then what I'm going to do is I'm going to change the color of the ink here. Then what I'm going to do is I'm going to heat this up. I'm going to heat my solution to... I can't even see the pen for this orange. There it is. I'm going to heat the solution to 50. How much can I then dissolve at 50 degrees Celsius? Looks like I can do this much. So, if I just heated my solution without adding any extra in there... So I heated my solution and it ended up over here. This is where we ended up. In other words, at 50 degrees Celsius and 30 grams, I would have an unsaturated solution, right? Because the solution can hold at most like 85 or so. But I only had 30 in there, so it'd be unsaturated. Now what we're going to do is we're going to add all that we can hold. So I'm going to go all the way up to 85. And then we would get a saturated solution again, right? All right. Let's assume we've attained perfect saturation. That is, everything is dissolved that I can, but I don't have an extra little bit of solid at the bottom. That's theoretically possible. It's practically not possible. We could undershoot it just a little bit and it'd be okay. And now what I'm going to do is I'm going to say, okay, instead of heating our solution, what happens if we do this, if we cool the solution? Back to 20. And I'm writing this in parentheses, dissolved completely at 50 degrees Celsius, because we dissolved everything, but remember, there was no solid left at this temperature. And what we said before on the previous slide was that we need a solid for recrystallization to occur, because if there isn't one, it won't, right? So if you've dissolved everything and then suddenly your solution doesn't have it doesn't have the temperature requirement to have that much stuff dissolved in it, you get an interesting result, and that result is called this. You get what's called a supersaturated solution. And the only way to do this is to do what we described. We take a solution and we heat it up to a high temperature and put lots of stuff in there so that it's saturated, but only just. And then you cool it down. And what should happen is that you should just start making a solid. But if there's no way for that to happen because there's no solid already there, you get to observe the supersaturated state. And the supersaturated state is very aesthetically pleasing. And so we're going to show an example of this here. So a supersaturated solution looks like any other solution. I hit the wrong button. Sorry, hold on. All right. A supersaturated... That's not what I meant to do. Slides. What are you doing to me? There we go. Okay. And so what happens in this case is that if you introduce a solid and allow it to crystallize, you get some very interesting phenomenon, and we're going to watch that here. All right, here we go. You can see in the reflection here the instructor who prepared the solution. He's grabbing a piece of sodium acetate here, and he's going to put it in the container. This solution is a super saturated solution of sodium acetate. And the instant that you add a small amount of solid, this is what happens. It's very cool to look at. Sodium acetate is one of those weird substances that it's extremely soluble at high temperature, but it's very insoluble at low temperature. And so if you heat something up to like almost boiling, dissolve a ton of this stuff in there, and then let it cool to room temperature, it can't recrystallize because there's no solid. And then the second that you put it in there, it recrystallizes back out, and it looks very cool. I have another video that I like to show you. It's this one. Let me make sure that captured correctly. Okay. And this is just sodium, super saturated sodium acetate solutions, where if you put in something that is coarse enough, like a stick or your finger or something, it will cause it to crystallize. Watch that when she puts the thermometer in, it doesn't start crystallizing right away, because there isn't a surface that's rigid enough for the crystallization to occur. But fingertips do it very quickly. Now, there's still water in here. It's just trapped in the lattice of the sodium acetate. So when you break it open, you can kind of see that it's still shiny. There's still water in there. But because there is so much sodium acetate in there, and the crystal is very low density compared to the solution, when you pour it, it expands very rapidly and crystallizes, and you get these really weird structures. And it's very bizarre to watch. It's super cool. Now, if you aren't careful with it, well, I'm waiting for them to do it. Like, things like this will happen. And you just pour it on surfaces. It might crystallize on its own if you agitate it enough. Generally speaking, it doesn't, because you need to have some rough surface to induce crystallization, which is why they're touching it with their fingertips. Oh, you forgot a spot. There you go. The end. And I've shown that video to my students 374,816 times. Because I'm sure I'm the only person that actually watches this video. Yeah, all the comments are from 11 or 12 years ago, so. All right. So that's a super saturated solution. So just to let you know that that sort of phase exists, you can do the same thing with things like water and freezing or boiling. So you can get a superheated solution where something tries to boil, but the gas can't find a place to collect, so the water just gets hotter and hotter and hotter and hotter. And then if you agitate it, like, the water immediately starts boiling and it may, like, erupt from a pot if your pot is too smooth. That is a thing that can happen. Same thing with freezing. You can get a super cooled solution where it doesn't freeze, but then you give it the opportunity to by adding, like, a nucleation site or whatever, and then it freezes instantly. Trying to think of when we'll do the super cooling one. I think we do that in 162 now. So you might get to see that actually in 162. All right, back to our discussion of solutions. We're working with aqueous solutions. Nothing super new or exciting here. I don't know why this isn't advancing. Oh, it's because I have two cursors on the screen. One was in another window. I was clicked on OBS. So Aqueous Solutions, no big deal. And then I don't care about those questions, so I'm going to skip them because I don't care about you finding a threshold for soluble or insoluble. Oh, excuse me. Something will be soluble if it looks soluble. Something will be insoluble if it looks insoluble. That's good enough. So let's go over the solubility rules, and then how much time do we have left? Oh, we have 30 minutes, so I might be able to get to concentration. All right. What will dissolve in water? Really, the only way to figure something out is to do the experiment. However, people have done the experiments for you. And we have tabulated that all into a table that you'll want to use this table on a quiz. So have it handy. And it looks like this. This is a very small segment of like the total solubility table, because there are tons of stuff out there, and this is just a small segment of them. But these are the common ions in ionic compounds that we have. And the way to use this chart is to find an ion in the first column over here, and then see if it matches an exception. If it does not match an exception, it's whatever chunk you were in, either the soluble chunk or the insoluble chunk. If it matches an exception, it is the opposite of whatever you were in. So, for example, we know table salt dissolves in water, but we'll look at this problem anyway. If we go back to Unit 9, we can figure out what ions sodium chloride will split into, so there they are. And now we just want to look up in the table if either of these entities appears. And so here's chloride, and then here's sodium in group 1A cations. These are both soluble. Are there any exceptions to chlorides? The exceptions are if I'm paired with silver, mercury 1, or lead. Then it would be insoluble. But sodium is not any of those. So we would say that sodium is soluble. Or sorry, sodium chloride is soluble. We do the same thing for group 1A cations. Group 1A cations are soluble. No exceptions. So anything with sodium paired with it will be soluble in water. Let's do another one just to get the idea here. So I'm going to do, let's see here. We're going to do barium hydroxide. So let's look at what this splits into. So we got barium and hydroxides. And if I look on this chart here, this is the first one I see. So hydroxides are insoluble unless they are paired with group 1A, ammonium, calcium, strontium, or barium. There you go. So instead of being insoluble, this is soluble. Oops, I wrote off the screen here. So that's how you use the chart. Now, if you have your notes handy, you have like the slides downloaded, scroll them to this slide. This is slide, what slide is this? This is slide 14 in your notes, or in the slide printout that you might have. Just have that handy on your monitor or another monitor, because when we go to these questions, these like over here, you're going to need that chart. All right. Now, the solubility chart is not the only thing that we govern solubility by. For substances that are liquids, for example, things like cooking oil or gasoline or water, they have much more complicated formulas that don't fall, and they aren't ionic, for one. And they form solutions that may be soluble or insoluble as well. So what we need to understand is how this works. In an ionic compound, we have charges, right? So sodium has a positive charge, which is kind of hidden right here, but you can see it. And then chloride has a negative charge. It turns out that water is partially charged. It's not entirely neutral. We're going to talk about this in 161, but water has a property called polarity. And you could think of polarity as partially charged. And so what ends up happening is that water, being polar, having a partial charge, will interact with other things that are either charged or partially charged. So water molecules will interact with each other. Water will interact with sodium chloride because it's charged. Water will not mix with things that are completely nonpolar and have no partial charges on them. So for instance, grease and oil, such as like from cooking, for instance, are nonpolar. If you pour water into like a greasy pan or pot that you've used for cooking and you just let it sit on the counter and then pour it out, you don't really do a very good job of cleaning it because all of the oil either skims to the top or remains stuck on the bottom. It doesn't dissolve. We're going to talk about this in a lot more detail again in 161, but the gist of this is that if you have something that's polar and you mix it with something that's also polar, they will dissolve and you make a solution. But if you have something that's polar and mix it with something that's nonpolar, they do not form a solution. They form separate layers. So if you pour water into, like, say, cooking oil, you make two layers. The top layer is the oil because it's less dense, and it just never dissolves. This is why, like, Italian dressing in your refrigerator has two layers, and you shake it so that you can put it over your salad, because both layers are delicious. However, they separate out naturally because of these intermolecular forces. The other possibility is that if you have something that's nonpolar with something else that is nonpolar, those will mix just fine because there's no charges to interact with, so everything just mixes because it's just there. It exists. And so we call this like dissolves like. So polar plus polar is a soluble mixture. Nonpolar plus nonpolar is a soluble mixture. But polar and nonpolar together do not work. So don't pour water into a gas tank because the water will not dissolve in the gas. Alternatively, if it's something that you really, 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 really hate, this will kill their engine because their engine will just take the water. The water's more dense than gasoline, and it'll sink to the bottom, where it will then feed into the engine and cause it to shut down. If you really, 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 really hate them, use sugar instead. You didn't hear it from me, though. All right. On the board, I have two liquids. I have acetone, which is nail polish remover. It's also used for other things, but that's the primary one that we use as consumers. We're going to pour it in water. Will acetone be soluble in water? What do you think? Yeah, if you own a boat, yeah, that'll do it too. If you flood your engine with water, especially salt water, yeah, that's no good. You don't want that. Keep that engine dry. So since they're both polar, we would expect these to mix. And they do. What about these two? Of cooking oil and carbon tetrachloride. Well, they're both nonpolar, so yeah, those will mix together. What about water and carbon tetrachloride? So if I did this, would they form a mixture? Well, water is polar, CCl4 is nonpolar, so this would not make a mixture. All right. For the solids, you have to go back to the chart. So what I'm going to do is I'm going to give you like a minute or two to look this up. What I'm going to do, hold on, let me hide this real quick. I'm going to put the 3 on the screen. You can tell me which ones are. There we go. That's what I want. All right. So I'm going to write the 3 substances on the screen here. I know you have these in your notes, but just don't look at your slides real quick. And then we'll just do this. And I can turn PowerPoint back on. There we go. All right. At the top, I've written 3 compounds. What I want you to do is look up these 3 compounds in the solubility table. And I want you to tell me, will it dissolve in water? Okay, so number 1, barium chloride. Number 2, calcium carbonate. Number 3, ammonium phosphate. Go ahead and look these up. I'm going to give you like 3 or 4 minutes to type in the answers in the chat. And then we'll go over them together. All right, 1 more minute. We'll go over the answers. All right, let's go over the answers. So, with barium chloride, if I go back to the chart over here, Let me clear all of this off the screen here real quick. So I'm looking for barium or chloride. Here's chloride. Is barium one of the exceptions? It doesn't look like it. So barium chloride would be soluble. So we would write yes. What about for calcium carbonate here? Would calcium carbonate be soluble? Let's go back to the chart. We'll clear the text here. So I got to find either calcium or carbonate. There's carbonate right there. Is calcium an exception to it? No, so therefore it is still insoluble. So when we go back to this slide, we would say, no, calcium carbonate is not soluble. And then ammonium phosphate, you probably saw that ammonium was the soluble exceptions none. So this must be soluble. Anything with ammonium will be soluble. All right. One more set of these. We'll have you do these. I have some polar versus non-polar questions, and then I have a trick question down here. It's not really a trick. I just want you to think about this carefully. So the first two are like dissolves like. The next four are solubility table, so go check the solubility table for those. And then tell me what you think about sodium chloride and benzene. Would that work? Hint, you have enough information on the slide to correctly answer that. We'll see if you can put it together. I'll give you 5 minutes. We'll go over the answers, and then we'll just stop there. All right, one more minute. We'll go over the answers here. All right, let's go over these results here. So I've got nonpolar and nonpolar. Like dissolves like, so those will dissolve. What about oxygen in water? Oxygen's nonpolar and water is polar, so these don't dissolve. Now, that's interesting. Oxygen is insoluble in water. How do fish breathe? Well, remember that something is insoluble if it's not if 0 of it dissolves. It's that if you were to put something in there, most of it wouldn't dissolve, like by far. Most of it wouldn't dissolve. And it turns out that with oxygen, very, 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 very little of it actually dissolves. We're going to talk about this in a much more detail in 161 and 162. But for our purposes, this is correct. Nonpolar oxygen does not dissolve in water, so it's insoluble. Sodium nitrate in water. So sodium and nitrate, both of those are soluble in water, no exceptions. Same thing with potassium, so it's soluble. Chlorides are normally soluble in water, but when you pair them with lead, they become insoluble. Barium hydroxide, I forget. We're going to have to look that one up. Where's my table? There it is. So here's my hydroxide. Barium is an exception. So therefore, this one would dissolve. And then we have the tricky one. So somebody mentioned in the chat that sodium chloride is like polar and benzene is nonpolar. And that's actually a great way of thinking about it. So if sodium chloride dissolves in water and water is polar, you could treat this like a like dissolves like, right? So this would dissolve in something that's polar. And in reality, it's ionic. And ionic is just very, 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 very polar. Like, so polar that it has its own category. And benzene is nonpolar, so this would not dissolve. If you drop table salt in benzene, it would just clump at the bottom. So, very good. All right. Let me check how many slides we have left, because we can do all these. Yeah, we can do this tomorrow. There's only 20 slides left, so that's what we're going to do. We're going to do all the calculations and stuff tomorrow. We might end up talking a little bit about the lab on Wednesday. Remember, Wednesday we have a class this week because it's a review for exam number 2. On the solubility chart, it says S is insoluble. Uh-oh, what did I do? Oh, for potassium sulfide. Okay, so we can go back and do that one real quick. So let's erase. So that's not erase all. Sorry. So you're right. Sulfides are insoluble. But potassium is group 1A. So it's an exception. So it becomes soluble. So K2S would be soluble. And it's because of the potassium part. Sorry if I zipped right through that. Oops, what am I doing? There we go. So let me put the bookmark back over here. And then we'll go back there. And we're all done. So, last remarks before we call it a day. So, quiz number 8 is due tonight. Closes tomorrow. Make sure you get that in. And then there's an exam on Friday. I'm going to go and post the last quiz. Make sure that everything is all open so that you can do that after tomorrow's lecture. And use that information to help you on the exam. And then we have a review session on Wednesday, so if you have any questions, feel free to bring them on by. Happy to go over them for that period. We'll talk a little bit about the lab then, too. Otherwise, that's really all I have, so... yeah. Have a good one, and we'll see you tomorrow. Take care.